When we're talking about circuits, we're going to start to talk about some of the elements that you would actually place within a circuit. Circuit is just a potential source that is connected through a wire, and you can put various what we would call elements into this circuit. The ones we're going to typically deal with in this class are voltage source, resistors, light bulbs, pretty much a resistor, but sometimes you have a distinction. The wire that's in the circuit, as well as a switch. There's many more. These are more or less what we're going to deal with within this course. In order to represent the voltage source, you will typically see this. You will see two terminals represented by a long line and a small line. The longer line represents the positive, and the smaller side would represent the negative side. You don't always see the positive and negative written, but you typically see a voltage source designated by what you would see there. That would be a battery. In some cases, maybe it would be a wall outlet. Sometimes there's different designations, but typically if you see that, you have some kind of potential difference. You have a voltage source. A resistor, if you were to see a resistor in a circuit, it's essentially just written as a squiggly line. And that's showing you that you have some kind of resistance. There's an appliance, a television, a blender, a computer, a cell phone charger. You have something resisting the current in the circuit at that location. If you have a light bulb, you pretty much have what looks like a resistor that has a little circle around it. Typically looks like that. You probably have something near the bottom, and then that will go out to the rest of your circuit. But a light bulb, pretty much a resistor encased in a circle to represent a light bulb. The wire in a circuit itself is just the line that you see. Simple enough, hopefully. And a switch. You have two types of. We have one type of switch, but we have two orientations. We have a closed switch, meaning that if you have this wires on either side, well, this switch here is closed because, as you can see, it is connected these two sides. It's closed. Current can flow through here. If, however, this switch was open, what you would see is something that looks like this. And as you can see, it makes sense. The switch is now open. There's no pathway for electrons to flow. If it's an open circuit or an open switch, you will not have a flow of current. And that's something we'll talk about in a second. Important to realize the main things we're going to deal with: voltage source, resistor, light bulb. You could also see a light bulb represented just by a resistor, but these are kind of interchangeable. The wire, anytime you see a line, just the wire within the circuit. And you have a switch. Closed switch, it's obviously closed. Open switch, it's open. You can't have current flow through an open switch. So that brings us to, well, what is the difference between an open circuit and a closed circuit? Well, if you think about the switch, a closed circuit would be, an open circuit would be if you had some kind of potential source, some kind of voltage source. I don't know, maybe you had a resistor in here, and at some point you have a switch. If this switch is open, well, the whole circuit is now open. If the circuit is open, you're going to have electrons trying to leave the negative side, travel through, but they hit the open switch and they can't jump across. They cannot jump that gap and continue to travel through. Conventionally, we would say the positive charges will reach this dead end. They will not be able to jump across and then travel to the negative side. Again, that's the conventional current versus actual current. This would be an open circuit. Hopefully that makes sense to you. It's open. The switch is open. There's no pathway for electrons to flow from one terminal to the other. A closed circuit, hopefully you see where this is going, but a closed circuit would be if you had a voltage source. You may have a resistor or something in the circuit. However, now the switch is closed. My switch is closed, then my circuit in this case is closed. There is a pathway for electrons to flow from the negative terminal to the positive terminal, or if you're going conventionally, current can flow from the positive side to the negative side. So this is the main difference between an open and closed circuit. If you think about this, this was a light here. Well, the light will be on in a closed circuit because you have a potential source that's connected to the bulb or whatever the appliance you have plugged in, a television, a cell phone charger, a computer. Here, you're not going to have that because you don't have power being transmitted to this resistor because your voltage source is not present. Well, it's present, but it's not actually conducting any current between the terminals. So an open versus a closed circuit, hopefully that's not incredibly difficult. When we start to talk about circuits, we're going to speak mainly with regard to resistors. It's important to realize we have two types of resistor orientations within a circuit. There's the two types are resistors in series or resistors in parallel. You can probably immediately see there's a difference between these two. The main difference is, if I speak in terms of convention, as positive charge travels through your circuit, in a series there is essentially one path. Any positive charge leaving the positive terminal, again conventionally, must travel in one path. It has no other options. In series, each resistor comes one right after the other. It's important to note here as well, just because I have an angle here, that's just kind of done to keep our, what we would call a schematic diagram, which is how you represent a circuit. It kind of just keeping our schematic diagram nice and simple, kind of clean looking. But this angle here does not mean anything. That could mean maybe, I don't know, it's the corner of a room and the wire is bent. Maybe I just shorten this up so I could fit it on the page. But this is telling you have a straight, direct path. The current must flow through every single resistor. In series, boom, run one right after the other. If you think about a series, like a TV series or a movie series, each movie, each episode in a series will come one right after the other. You should watch the previous one before you watch the next one. So very similarly, you must pass through each previous resistor before you travel through the next resistor. Parallel is a little bit different. If you see that there's only one path here in series for the current to flow, if you look over here, current traveling from this terminal to this terminal essentially has three different options. I can travel here, and when I hit this junction, I have a decision to make. Do I travel through this resistor and return? Do I keep going, travel through this resistor and return? Or do I go all the way to the top and come back down the other side? In either case, I'm only passing through one resistor as an electron, or I'm sorry, in convention, a positive charge. I will only pass through one resistor. Hopefully you realize it's not a conscious decision. It's based on physics, and we'll talk about what will make a charge choose one path over another. But for now, realize in series, one resistor right after the other, one path through which current can flow. Parallel, multiple paths. And even though I have three resistors here, every charge that passes through this circuit will only have to pass through one of these resistors. You're not going to have current that's going to go here, decide to go up, travel around, go in loops, come around. You're going to have it go from here to here. It wants the shortest, least resistive path possible to get from one terminal to another. So that's the main difference between series and parallel, which brings us to the main topic you need to be able to take away from this video, and that's the idea of what is called equivalent resistance. Sometimes it's referred to as total resistance. What this means is if I have resistors in a circuit, whether that be in series or in parallel, we need to be able to say, what is the total resistance in this circuit? So we take a look here in my series diagram here. I have two resistors, a 5 ohm resistor and a 2 ohm resistor. They are in series, so any current traveling from this terminal to the opposite terminal must pass through both. In series, when we want to determine the total or equivalent resistance for the entire circuit, luckily it's pretty simple. In order to calculate that equivalent resistance, it's very simply the resistance of your first resistor plus the resistance of your second plus the third, and so on and so forth for however many resistors you have in series. In this case, if we take a look, I have two resistors. I have a 5 ohm and a 2 ohm. So in this case, I will only add my first and second resistors. So if I want to determine what my equivalent resistance is, if you bear with me for 1 second. If I would like to find my equivalent resistance for this, if I follow this equation up here, well, my equivalent resistance will equal the sum of my resistances. So I have a 5 ohm, which is my resistor 1, and my second resistor is a 2 ohm. So my equivalent resistance for this small, very simple series circuit will quite simply be 7 ohms. In series, luckily, it's pretty easy. We just add up our resistances, one right after the other. Parallel is a little bit of a different story. The charges have obviously more than one path to choose from, so that needs to be taken into account. The way that is done is, instead of directly calculating the equivalent resistance by adding the first resistor plus the second resistor plus the third resistor, is to actually go ahead and take 1 over your equivalent resistance, which is essentially the reciprocal of your equivalent resistance, and that's going to equal the sum of the reciprocals of whatever resistors you have in parallel. So 1 over resistor 1, 1 over resistor 2, plus 1 over resistor 3, and so on and so forth. So what we have here is 1 over my equivalent resistance is going to equal, in this case, 1 over 5 plus 1 over 2. Now it's important to realize here that we need to make sure that our answer is 1 over our equivalent resistance. So if we wind up with some fraction, we can't wind up with 2 or 3 or 4 in the numerator. You must have 1 in the numerator, and the denominator will therefore be your equivalent resistance. If you bear with me 1 second, let me get my calculator out. That will make things a little bit easier. All right, so if I have my calculator, I'm going to show you the easiest way to do this. This will probably be the best thing you take from this video. If I take 1/5 and I add to it 1/2, which again, all we're doing is adding up the reciprocals of our resistors, what I wind up with is 0.7. If you simply add your reciprocals together and raise your result to the -1 in your calculators, that will give you your total equivalent resistance. So add your reciprocals together. Whatever answer you get, raise that to the -1. So to show you, if I raise this to the -1, what I wind up with is 1.4, let's say 1.43. So my equivalent resistance, 1.43 ohms for this parallel circuit. Again, we're adding the reciprocals. Easiest way to do this, add the reciprocals of your resistors, raise it to the -1, and what you get will be your equivalent resistance. So I slide this out, series, add up our resistances, R1 plus R2 plus R3, so on and so forth. Parallel, the reciprocals, and the easiest way to do it in the calculator, add your reciprocals, however many you have. I could have 5, 10, 50 of these resistors in parallel. You add up all your reciprocal resistances, raise that number to the -1, and that will give you your equivalent resistance every time. So just to show you a few examples before you attempt the night's homework, let's take a look at example 1. Well, in example 1, we are given 3 resistors, and hopefully you realize right now that this orientation is in series. Well, if this is in series, hopefully you remember that the equivalent resistance in series for resistors will be R1 plus R2 plus R3, etc., etc. So in this case, it's very simply 3 ohms plus 2 ohms plus 4 ohms, which is going to equal 9 ohms. So for your first example, it's quite simply 9 ohms. You're just going to add 4 plus 3 plus 2. Series are very easy in terms of finding your equivalent resistance, so hopefully you're starting to see what you need to do for that. The second example, not series, hopefully you realize this is in parallel. How do you know? Well, if I'm a positive charge and I'm leaving here, well, I have 3 options to get through this circuit. 1 through the 3 ohm resistor, 1 through the 2 ohm, 1 through the 4 ohm. Again, please realize you're not going to have any kind of charge go through the 3 and then go through the 2 and then the 4 and back through the 2. They want to get to the other terminal of the voltage source as quickly as possible. Think about it like if you're trying to get from work to home. All right, well, if you had to sit through a little bit of traffic here, once you get through, you're going to go home. You're not going to decide to go down, drive down another highway. You want to avoid all this resistance. You don't want to go through that. So you'll go through, wherever you travel, boom, you'll immediately return to the other side of the terminal. Electrons are going to want to do the same thing. So just realize, I'll reiterate this several times, you're not going to have any charge that wants to travel through all this resistance. Nobody likes resistance. Your charges aren't going to want to be resisted. They're going to want the easiest path. The path of least resistance, so to say. So since we have 3 resistors in parallel, hopefully you remember at this point, if we take a look back, that parallel resistors are the reciprocals of the resistors in your circuit. And if you want to take the shortcut, add up your reciprocals, raise your answer to the -1, and you should get what is your equivalent resistance for a parallel circuit. So I have 3, 2, and 4. So if I want to take a look at this, my equivalent resistance will be 1 over 3 plus 1 over 2 plus 1 over 4. If I plug that into my calculator, I should find that, let me clear that, 1/3 plus 1/2 plus 1/4 gives me 1.08, and I must raise that to the -1. And what I wind up with is a resistance of 0.92. I'll round that to. So 0.92. Actually, let me backtrack there. Just, oops, apologize. Let me backtrack so I don't confuse you. I believe that, what did I have before? Let me see. 0.852 is what I originally had. So 0.852. And when I raise that, well, I'm going to backtrack entirely right here before I confuse everybody. Bear with me, please. Go away, 0. There we go. All right, so quickly again, I have 1/3. I apologize for any confusion. I will add to that 1/2. I'll add to that 1/4. And what I'll end up with is 1.08. So this whole thing equals 1.08. If I raise that to the -1, what I get is my equivalent resistance, which is going to give me 0.92. So 0.92 ohms, that's the total resistance for this circuit. Again, add up your reciprocal resistances raised to the -1. That will give you your equivalent resistance. We take a look at example 3. This is a little bit different here. What we're going to want to do here now, we see here we have, well, 2 paths to get through, but I have to go through this 3 ohm resistor for both. So if you take a look, you should note that these are in parallel because there's no one path which will bring me through both of these. And this one is kind of out here on its own. Some people want to take a look at this and say, well, if I go through here and here, oh, well, these are in series, so let me combine these by just adding my resistances. Well, the problem with that is if I add my 3 and my 2 to get 5, what do I connect that to? I have 2 things. I have to incorporate this 4 ohm resistor, but I also have to connect it to the potential source. So we have a problem here. If I combine these, I wind up getting one resistor with one wire that I have to connect to 2 different locations. And that's a dilemma. We have to avoid that. So hopefully you're starting to see that if I combine these 2 in parallel first, what I'll get is one resistor here, an equivalent resistor, which is then in series with this other one, which then kind of eradicates all the problems that I had of trying to connect one equivalent resistor to 2 different locations. So maybe a little bit difficult, but hopefully you're seeing that I can't combine these 2 until I combine these first. Once I combine these and I effectively replace them with one resistor of equivalent resistance, it's then in series with the 3, and I'll show that right here. So the first thing we need to do, if I want to combine my 4 and my 2 ohm resistor, is, since they are in parallel, add the reciprocals, 1/2 plus 1/4, and that should give me 1/2 plus 1/4. I wind up with 0.75. What I must do to that number now, since it's in parallel, is raise that to the -1. So if I raise that to the -1, what I wind up with is 1.33. So my equivalent resistance is 1.33 ohms. But that is the equivalent resistance of these 2. So if I were to combine these 2, what I'm essentially getting here, if I were to redraw this, is I have my 3 ohm. And what I've done is I've essentially combined both of these to form what has a resistance of 1.33 ohms. This up here still has 3 ohms. So hopefully now you can see that what I've done is combine these to an equivalent resistance of 1.33, and it's now in series with the 3. So if I want to find my equivalent resistance here, now that I've taken this a step forward, they're both in series, so it's quite simply 3 plus 1.33, which will give me a total equivalent resistance for this, which is more of a complex circuit, which we'll analyze in more detail later. A total resistance for this complex circuit of 4.33 ohms.